thanks for coming tonight. I know it's taking time out of your evening is always a trade-off, but I appreciate you being here and for using Python to solve problems. So my abbreviated bio is I've spent the majority of my career working on data tools. I think people often call me a data scientist, but really I've spent most of my time making tools for the data scientists and have spent comparatively little time actually doing data science. Although I secretly want to be doing more modeling and data science, but find myself gravitating toward the tool making. I did several years ago make an honest effort to go back to grad school and get a PhD in statistics, but I dropped out in favor of working on tools. So I guess as context for this new project, during the first part of my career, when I was a QR, is where I got interested in data tool making in the first place. I found myself in quant finance, basically writing SQL and using Microsoft Excel and looking for solutions for that, not only for building production code that can be run every day, but also doing interactive research and just ad hoc analytics. And so pandas was kind of a solution to both of those problems, to be able to solve production, build software effectively, but also move work out of the SQL and Excel workflow that I found myself in the middle of. So we all love Python, and the world is a lot different than it was seven or eight years ago when I started out programming in Python. It used to be that you had to have all these arguments about, can we trust Python in production? Is it a serious programming language? Maybe we should be doing Java or C++. And thankfully, we're not having as many of those kinds of arguments anymore, in part because the tooling and the software development tools, the data tools have become a lot more mature, and so big companies find it a safer choice because there is a mature ecosystem of tools. There's also a community of supportive developers. There's resources for learning how to program in Python. And generally, there's also teams of data people that have track records now of using Python over a period of years that have been successful. So back in 2006, 2007, there wasn't that track record. It was a chicken and egg problem where there were no successful teams that had multi-year stints of doing Python data stuff. People were just starting out to do it, and so if you were choosing to solve those kinds of problems with Python, it made you seem a little bit weird at the time. But now it's viewed as a safe choice, and for lots of good reasons. But Python has definitely struggled to move beyond the medium data types of problems which fit. So I describe medium data as data that fits on one machine. I guess you could also call data that fits on one machine small data. But I think of small data as data that you don't have to be that careful about the size. So nowadays you can get machines with 2 terabytes of RAM. You can get nodes on EC2 with 2 terabytes of RAM. And so the problems that now are medium data are quite large, whereas even having 10 or 20 gigabytes of data used to feel like big data because you needed many machines to solve it. But if you do have properly big data, using Python is still problematic. And the way that data scientists usually get around the problem is by using another system to sample or aggregate the data and get it into a size where it can fit on one machine. So if you have a problem where you need to analyze the full fidelity data set, maybe you have many terabytes or a petabyte of data, maybe the things that you're doing with the data are not very complicated. I think a general trend that you see is the larger the data, the less sophisticated the analysis, largely just counting things when the data gets really big. But still, it would be nice to be able to use Python in a full-featured way, regardless of the size of the data. And some of the reasons for that, and I kind of generalized the world a little bit into these two categories of tools. And so there's been a chicken and egg problem in the Python community, that the class of tools tend to fall into these two categories. On one hand, scientific computing tools, and people have been doing scientific computing in Python since the mid-1990s. And part of the reason that we have nice things in Python is because there were a lot of grad students who were procrastinating on their PhDs and wanted to have an alternative to MATLAB. And so they invested heavily in creating and wrapping up all of the legacy scientific libraries, creating really good interfaces to high-performance computing tools, linear algebra, and all that stuff. Starting with SciPy in 1999, 2000, that era. NumPy itself is going to have its 10th birthday early next year, I believe. I don't know the exact date, but it's getting up, around 10 years old. But people have been doing multi-dimensional array computing in Python for many years. But if you look at, when people say big data in Silicon Valley, and it might be that big data is different depending on who you talk to, largely they mean data that's falling on the left side of this page, which is more heterogeneous, structured data that could be written in a CSV file or in some form of application log file. Increasingly it's JSON, and in a sense, work that's happened elsewhere, like outside of the Python community, has encouraged this, because application developers who are Ruby programmers or Python programmers or Node.js programmers, or they're in the Java ecosystem, they're all putting their application data often through the same pipe. It's landing in some distributed storage in data that's, let's just store the raw data in JSON, and then we'll figure it out later. And so the tools have rise to the occasion in the Hadoop ecosystem with MapReduce, and now it's more and more Spark. You have really good tools for analyzing such data with SQL code. And in general, this is how things have shaped out, or shooken out. And Python, great stuff over here. Less stuff on the left side. It is changing though. So if you look at Pandas was an effort to build an industry analytics toolkit using the Python's scientific computing stack. And if you look at Pandas, the library, part of the reason that it's grown so large is because it had to mind all of its own concerns. It had to build its own in-memory analytics engine, all of its own relational algebra, joins. It has its own CSV reader. It has its own interface with SQL databases. It implements its own data types, because there's data types that occur in the wild which are not found amongst NumPy's data types. It has to handle its own missing data, because NumPy doesn't have a built-in notion of missing data. And a lot of the reason that people stick with it is because of its API. And so the Pandas code that you write, it is true that every time you execute a statement with Pandas, it's immediately executing that operation. But you can also look at the Pandas code that you write holistically as a domain-specific language for describing your data transformations, your analytics, and all of your data work. And so, in a sense, a question that I get from people a lot is, Wes, I want to keep using Pandas, I just want it to work with big data. And that's a very complicated problem. And in a sense, the work that I'm doing now is to address that need. Now, meanwhile, there's lots of SQL engines, and the SQL engines often are created for some, for some problem domain, whether you're Facebook and you can have an engineering team build your own interactive SQL database. Some of them are, have originated in vendors. Some of them are open source. Some are closed source. And these systems have generalized to meet the needs of industry analytics in a lot of different ways, I'm sure you're aware of. And so, the big trend that I see, and will be the theme of this talk, is that in big data in general, one of the novel things with things like Amazon S3 and HDFS, Hadoop's distributed file system, is that it's decoupled the storage part of the problem from the other systems that are part of the equation. So you can use MapReduce with HDFS, but it used to be when people said Hadoop, they really meant HDFS and Hadoop MapReduce, whereas now you have a whole smorgasbord of computing tools which know how to read and write data to HDFS. They can also read and write data to Amazon H3, to HBase, to other storage engines that are all open source. And so it used to be you would buy a system that is vertically integrated. Your user interface is probably SQL. It has its own built-in compute engine, its own storage engine. So when you buy Amazon Redshift, you're paying for it as a service, but really you're buying into a vertically integrated stack of UI, compute, and storage. But in open source, these things are decoupling. So if you have your data, you can put your data wherever you want. You can bring your own compute, whether that's Spark or MapReduce or a SQL engine, and so hence the rise of SQL on Hadoop. But that leaves kind of the user interface being the area where there's been comparatively little invested, and a major reason for this is that the storage and compute is hard enough. And so, in terms of like Maslow's hierarchy of needs for big data, in a sense, user interface and the quality of the user experience of interacting with the data is the part that comes at the tail end of the equation after you've fully addressed the scalability and performance problems of the compute and storage systems. And so if you think about big data architecture, so how appropriate that we're at LinkedIn and I can have a big data architecture which uses Kafka, which was created at LinkedIn. But you see more and more systems like this where you have a lot of real-time data that's being ingested, landed in raw form, usually in JSON or some other flat format. You write an ETL job to convert the raw data, to clean it, to pull out the stuff that you're interested in, store it in a more efficient format, which is increasingly something like Apache Parquet, columnar, compressed columnar format. And then you consume that ETL data in some compute system. So I just put an analytic SQL engine here as an example. But if you think about these architectures, there's relatively little Python happening in them. And to choose Python at any stage of this architecture would come at the cost of performance or usability. And so usually what you see is that Python is happening down in this area where a lot of the work has already been done. You write a SQL query, you get the data back into a pandas data frame, and then you do your modeling, analytics, data visualization, whatever. And so the cool thing about the SQL and Hadoop systems that are being created is that their ability to address, they're getting better at dealing with more complex data. So it used to be, if you look at your big data architecture, that half of the work that's happening in your ETL jobs is taking data that isn't necessarily flat and normalizing it into a set of tables that can fit into a flat relational database structure. And with the addition of nested or complex type support to analytic SQL systems, is that you can analyze JSON data directly in place without having to go through that flattening, kind of unraveling normalization step. You still have, there's still some work to do. You have to infer schemas. That's a pretty hard problem by itself. But assuming that you can write down a schema for your data, and your SQL system knows how, has that schema support given your data, you can write queries that are very expressive that can analyze that data in place. And so Google BigQuery is my understanding is a SaaSification of Google's Dremel system, which was published about in 2010, which means that Google was doing analytic SQL on JSON-like data back in 2003 or so. And so there's a long history, and it's been shown to be a pretty good way of working with this kind of data. So the project I'm building, Ibis, which I started when I joined Cloudera a year ago, is a user interface layer. Well, it's a little more than user interface, and I'll explain. But really, it's intended to be the user interface layer for Python programmers doing industry analytics that hides away as much of the complexity as possible of the storage and compute problems, and enables you to do your Python work with big data without having to leave Python, or leaving Python as little as possible. So, that solves, I think that I didn't really have experience with big data systems starting a year ago. Like I was really a small and medium data kind of person. And so I looked at this and said, well, it's unfortunate that when you go from small and medium data to big data, you have to learn a whole use of tools. You have to climb a bunch of additional learning curves and learn a whole bunch of new systems. Whereas what you're actually doing with the data in a lot of cases isn't that complex. It just happens to be that Python isn't very good at talking to those systems and integrating with them. And so I sat down with various teams around Cloudera and said, well, how can we build a better synergy between, I didn't use the word synergy, but I'm using it now. How can we connect Python to big data systems in a cleaner, more efficient way to deliver the kind of experience that you would like to see, in the next, within the next few years. And so, for the purpose of this talk, I'm going to talk about two areas of, concrete things that we're doing with the project. And the first is to move SQL programming out of the SQL programming language and into Python, and in a way that looks and feels a lot like pandas. And so the other part of the problem, which is conveniently cut by the screen divider, is extending analytic SQL systems with Python code. Not just analytic SQL, but analytic SQL happens to be the target, but extending these big data compute systems with Python code in a way that doesn't trade away an unacceptable amount of performance or usability. So I'm going to talk about the Ibis DSL, which is the deliberately pandas-like expression layer, which the design goal out the gate was to look at the SQL programming language, and let's make sure that anyone can take their gnarliest, craziest SQL, 100, 200 line queries, and break it apart into composable, reusable Python statements. So that anything you're doing in SQL can be fully ported to Python. So if you look on the website, there's actually a new document which I wrote last month called Ibis for SQL Programmers that goes through every granular SQL relational concept and shows how you can map those SQL concepts onto the equivalent Ibis calls. So part of what I did there is I looked at not only real world customer workloads, queries. They would send like this crazy 200 line query, and you see what people are actually doing with the data. There's also benchmark suites to evaluate the completeness of SQL engines that you can use things like TPCH and TPCDS if you're database junkies in the room, that you can use to really stress your ability to generate complex SQL. It did target Impala, and we're focused on developing tools that will work well with Impala for a couple of reasons that I'll explain. But the general SQL generation toolchain inside Ibis is very general purpose. And so I'm looking for collaborators, which might be people in the room, to build support for other analytic SQL backends. So high on the list of wants in Ibis are Redshift, Presto, Vertica, Postgres, which is not really analytic SQL, but if you do some Postgres and some Redshift, they kind of help each other because you're all working off of basically a common SQL dialect. And so the way that the project works is you write Python code. It hides as much as possible of what happens down in the compute layer. We are working on tools to extend analytic SQL systems with user-defined Python functions, and that will be the second half of the talk. Now I'm going to go into a demo and show you what the DSL looks like a little bit in about 5. I need to come up with like a 3 or 5 minute demo for talks, but if you do look at the Ibis for SQL programmers, it's broken down, and so even like weird stuff like exists, subqueries and things like that, like all that stuff is in here and shows the equivalent Python code. And so the intent is to be very, very pandas-like. So while I can't promise to exactly port the pandas API to an expression language that compiles to big data systems, the idea is to get as close as possible, or at least to take every API and concept from composable, R or pandas-like tools and make them available, executing on a different backend. So, API and all that stuff there. So let me try to record the screen for a couple of minutes. And so I'm also operating a blog, which I haven't posted on, I know, since mid-September, as I've been traveling, but is both a development kind of developer blog as well as use cases and examples of using the project. So I'm going to use the SQLite Ibis interface. So I have a data set containing, which you can download from the blog, it's linked to from the blog, containing the Crunchbase data set, slightly outdated, but that's because they won't give me access to the latest one. Like I don't know why. Maybe if you know anyone at Crunchbase, you can tell them like Wes wants the data. Like he wants the data. Like he's going to write about it, like popularize Crunchbase. Like I think it's a great data set. And so if you look inside it, it has a set of tables. And the idea with the project is you grab. Let's look at the rounds table. So a table in Ibis speak is like a pandas data frame, except the data is not on your computer. And so anytime you build an operation, let's say rounds : 5, that's just like the equivalent pandas operation. Whenever you try to examine the expression you create, Ibis takes that expression, compiles it to whatever backend target, runs the query, and returns the results in a pandas data frame. So effectively, what you're doing, you can also call the .execute method, which returns a data frame. And so any operation you perform returns the appropriate pandas object. So if you have a table expression, you get a table. If you say, let's see, if you look at rounds raised amount USD .sum, it shows you this is the total amount that's represented in the data set. And these are all expression objects that you can reuse. So here, when I call raised amount USD.sum, I get a double scalar expression. And so the fact that if you look inside the object and you're developing, there's a little expression tree which shows all of the operations that you performed on the data. So here's the column from this table, which has this schema, the sum operation, which produces just a single number. And so, but you could take this expression and say, well, really, I want to maybe group by rounds funded quarter, and then maybe aggregate with that expression. Let's call that, I'm not going to give it a name. So any aggregate expression you can put here, any grouping expressions you can put here, and when you look at this guy, you just get a total amount raised by quarter. And so you see here, if you suppose you wanted to group by quarter name, you'd have to actually transform the data set a little bit. So we can just do that right now. If we look at funded quarter, let's call strip on it because it's a string. And now let's do write to. Actually, I haven't tried this, so we're gonna see. Okay. So we strip it, do write to, which gives you the write to characters. And so we can take this guy. So let's call this quarter. And then I'll give it a name, quarter. Now group by quarter. And so now you get Q1 through Q4. You can pass a list of grouping expressions just like in pandas. You can put a list of metrics here, like suppose I wanted also to get the number of rows, so rounds.count. So there are some nulls in the data set. So if you wanted to do some cleaning, you could do, you can continue composing and adding operations. So I could say fill in A. Maybe I'll fill in A after doing the data merging. Fill in A, unknown, word. So we'll get on to something slightly more complex. So I look, so I have friends who started Node Analytics and work there, and so they have this query where they compute like the most successful investors based on whether or not they've had exits. So like the number of investments that they've made divided by the number of those investments that led to either an IPO or an acquisition. So you can go on and look at this example on the blog. You see there's some munging here where you define what is an exit. You do a count distinct on that. You do a count distinct on the number on the company permalink, which is how companies are identified, and that's after doing a join of investments on companies. And then finally, you have an inline view, and you compute the acquisition rate by investor. And so what's nice about the Ibis version of this is that you take this nested SQL query with a bunch of embedded expressions, and you can break it down into a set of reusable expressions. So here's just to walk you through what this looks like. So there's some cleaning that you do on the investor name. So you fill in A's, you give it the name investor name, you compute your two metrics of interest, so the number of unique companies for each investor, their statuses, so either if they're IPO or acquired, so use the isIn function just like pandas, do a Boolean if else, so null out ones that are not IPO or acquired, call count distinct on that, which is the nUnique function. Then do your join. The joins are all reusable, and then you group, aggregate, and then use the mutate function inspired by dplyr to add the acquisition rate column to the aggregated table. So you run that, and you get for each investor an acquisition rate, and you continue going and say, well, I think I called that stats2, yeah. So then you can take, forget about all that other stuff you did. Now say, I want to filter down to only investors that made over 100 investments, sort by acquisition rate in descending order, and then you get your top 20 most successful investors. And so with Ron Conway just leading the pack by a significant margin. So anyway, SQL, we're feature complete with SQL, and that was the first major part of the project. So if you do use the library and you find something that you can't do in SQL, please make a bug report. That's my attitude toward it. All right, so I did the demo already. So there's some interesting stuff going on in Impala that we're, Ibis is helping steer development in Impala, and the main thing that's happening there, and it's going to take some time, is how to extend a distributed computing system with Python and achieve good performance. So if you think about the problem schematically, you want to take Python code, which is at the UI layer, and move that Python code into the compute layer and have it run as is without need for some translation or compilation step. And there are a lot of compilation tools for Python, but they're limited. And if you have libraries that you've built up over the period of years, which are written in Python, there's no chance of translating them or compiling them. They have all of your domain-specific logic that you want to run in a distributed environment. You'd like to be able to just move that code there and have a way to extend those systems in an efficient way. This is extremely hard, though, which I'm sure many in the room are aware of this, that extending any distributed computing system usually involves implementing user-defined functionality. So, let's say, you're using Presto, and there is a way to extend Presto with your own code, but you have to write it in Java. There may be a way to write, Python functions or extend Presto. You can now extend Redshift with Python functions, but they're extremely limited. And so what I call the extension with a language that is not the implementation language of a compute system, so I call that the external language protocol. So usually, sometimes you can have an external language protocol which is embedded in the system, and so you've seen in big data, I know in LinkedIn, like JRuby and any of the J kind of implementations of Java implementations of dynamic languages got really popular because you could write UDFs not in Java. If the processes that execute the code live outside of the host system, usually you're dealing with a pretty serious performance bottleneck. And so if you write UDFs in Redshift, you're basically making remote, inter-process calls between the Redshift master process and an external Python process, and usually you're operating on a one row at a time data model, which I'll talk a little more about. The same issue is true of Spark. So if you're using Python with Spark and you write anything that can't be expressed as a data frame API call, you're dealing with pretty significant performance overhead. There's a lot of things you can do through a UDF interface beyond simple data transformations. You can also express a large class of statistical machine learning models as aggregate functions in SQL type systems. And so the reason that the UDFs are slow, and there may be other reasons, but typically it falls into these three categories of problems. And so the first and the biggest issue in practice is how the data moves between the host system and the external language. So if you're Python, it's how does, so if you're Redshift, if you're Impala, if you're Presto, if you're Postgres, how do you actually get the data that's flowing around this distributed runtime? How do you get it into Python? So that's what I call serialization overhead. There's also the computation model, and so with Python, it's generally accepted knowledge that you don't want to operate on one value at a time in Python. You want to operate on one array at a time, and the array should be as large as possible so that you can effectively be orchestrating very fast C or C++ code with Python function calls. There's also the question of how you call out into an external process, and indeed, inter-process communication or remote procedure calls can introduce significant overhead into any external UDF. So just looking at vectorization as one place where a lot of performance gets eaten up. So here's a SQL statement with a Boolean condition selecting one value for true, the true branch, x plus y for the false branch. And if you implement this in Python, and I'll explain this diagram. I don't know how many of you can read it, but so the x-axis is the size of the array that's being operated on. So this line right here is arrays that have 1,000 elements, and this is 5,000 over here. The green line is the one line, so that's the pure Python implementation of this sum with a Boolean condition. And so then the blue line, and so this speed up line right here is 50x speed up, this is 100x speed up, 150x. And the blue line is a naive implementation using NumPy vector function calls with temporary variables and everything. So, the simplest thing you could do, which uses all vector operations, and that, you end up around 50x speed up with large arrays. And so if you avoid temporary arrays and you use Python to generate C code, you get up to, the red line is the simplest Python implementation I can write, and then I, use kind of Python tricks to eke out another 50x speed up. But these kinds of speed ups going from scalar to vector operations in Python are very, very common. And so if you're extending a big data system with Python, you better have a way to do vector operations if you want your Python code to run fast. And so what we're doing to deal with this, not only the scalar versus vector operations, but the larger kind of general problem of how data moves efficiently between systems, in particular tabular data in analytical systems, is we are creating a shared memory representation for tabular data that can address JSON-like data in an analytic SQL system. So basically, you can hand off a blob of data, so a table or an array of data, to a Python process with as little conversion as little conversion or modification as possible. Our goal is to be able to hand off the data with no serialized or deserialized steps. So it's going to be as fast as you would get out of a mem copy through a shared memory region. Part of the reason why we're focused on Impala to do that, first of all, being among SQL and Hadoop engines, one of the best of the bunch. It's also written in C++, which is nice as far as native performance, being able to do runtime code generation to accelerate the management and moving around the data within the runtime. In particular, when you know that you have a Python UDF function call coming up. So there's a lot that you can do there to achieve native performance in that sort of C++ LLVM framework. Another reason is that if we improve, and we do at some point plan to improve the LLVM compilation toolchain in Python to address more and more complex data. And so there will be an interesting class of Python functions that can be compiled to LLVM, and those can be inserted directly into the runtime without need for any external any external data movement. So there's prior art on having a standard memory representation for at least analytic SQL systems. The Apache Drill project, if any of you are familiar with that, is another SQL and Hadoop. Not just SQL and Hadoop, but you can read from many systems, but it was initially designed for Hadoop use cases. It has a standard columnar in-memory representation of tabular data that can address a substantial subset of JSON. The same is planned for Impala. We're hoping that we can create a format that can be used amongst all of these systems. There's already been a standard way, at least in open source, of storing, an increasingly standard way of storing compressed columnar data. That's the Parquet project. But the thing you have to realize about, I don't know how much you all studied Parquet or columnar formats, is that there's an explicit trade-off in systems like or tools like Parquet to maximize the throughput that you're getting out of distributed storage. So if you're on HDFS or you're on S3, the bottleneck in doing analytics on data that cannot be all memory resident or all in RAM cache is the slowest thing is going to be the spinning disk hard drives. It's more and more flash, and so the trade-offs will change over time as increasingly everything is solid-state disks everywhere. But with these serialization formats, they're designed for that trade-off between I/O and CPU throughput. So compress and encode the data as compact as possible while also being able to blow it up into fully materialized in-memory form as you stream through the data to do analytics. Another problem with the columnar serialization formats is that there's not a standard data structure to put the data into. So if you look at the Parquet Java implementation, and I actually have not, so I'm not an authority on the matter, but basically data is getting serialized into native Java data structures. If you're in C++, well, there's not even a standard C++ implementation of Parquet. And so if you were in Python and wanted to interact with data in Parquet to have an efficient data structure to exchange among systems that know about compressed nested columnar data like Parquet, you'd be having a bit of a bad time. So this is a major initiative that I'm working on right now to create a standard data structure for in-memory data coming out of things like Parquet, but can be friendly for Python and used to move data around amongst these analytical systems with minimal serialization overhead. I actually, as of the last week or so, have an implementation underway that will all be open source. We're trying to come up with a name for the project. So as soon as there is a name, there will be a GitHub repo with a specification for the data structures and reference implementations. As soon as I'm not that embarrassed to show my messy C++ code to the world. But basically building it up to be able to create Python bindings, to be able to interoperate with systems that can emit, send, and receive data according to that data structure. So, highly technical, but the grand goal of writing more and more Python. And I think some people think of me as being like ideological about it must be Python or it's crap, but I don't really feel that way. I think Python is a really great tool, and the fact that you have a really accessible community of developers and tools and a learning curve that is not too steep, that building software in Python makes a lot of sense to reach a really broad audience of people who can now tackle data problems that they couldn't have, 5, 10 years ago. So I like other programming languages as well, but I think that Python is a really great place to invest and to have as a primary language for data teams. So anything that is blocking using Python to solve certain classes of problems strikes me as a real issue. And so you need to be able to extend these systems with Python code and to do it without trading away major performance. So having these common data structures is a key part of that, of solving that problem. So that's my goal, being able to solve big data, without leaving the Python notebook or whatever Python development environment you prefer. You want to be able to bring the software that you built in Python with you without having to throw it out completely. So that means being able to use the existing Python data ecosystem, tools like pandas, scikit-learn, NumPy, and so forth. You'd like to be able to use them in a big data environment without having to completely modify your workflow. Obviously, you do have to write your algorithms in a way that is amenable to the distributed computation model, but all the software that's been created for working at partitions of data locally on one node, you should be able to use that software without hesitation in a scalable big data environment. So that's all the slides I have, but I imagine there are some questions, and so I can answer questions for 5 or 10 minutes, and we'll stick around for a little while after the talk. And if anyone has more detailed questions about the project or wants to get involved, I'd be happy to talk.
If there are questions.
Oh yeah.
Can you still repeat the questions?
I'll repeat the questions, yeah.
Hi, do you have plans to integrate with Hive?
Yes. I'm not sure what the timeline will be, but if that's personally important to you, like I would love some help, but
So just to give you a background, I use MapReduce for a long time, and lately I'm doing a lot of relatively complex stuff with Hive streaming using Python, and that's it's a pain to configure, but you can pretty much do whatever you want. But if you add this level of simplicity that you have, break anything.
yeah. So I definitely I don't know what the timeline will be. I guess it's a function of like how much help I have, but I'm really keen to get basically. Trying to see if I can show you what the code looks like, but basically a lot of the work in the project for adding SQL support is mapping SQL built-in functions onto the Ibis like operation classes. And so the idea is like every SQL dialect is a little bit different, and so so maybe like whatever if Hive has like approximate median that uses count in sketch, you can map that function name onto the CMS median class. All the string functions, things like that. So that's the main work. It's a lot of legwork to wrap all the built-ins, but adding Hive support wouldn't be too terribly much work. So it's wrapping built-ins, adding test coverage, and then also adding support for. You guys Hive, I imagine a lot of Hive uses for ETL. And so like a big use case for Ibis is ETL workflows. And so yes, analytics, big data, interactive analytics, but also like to be able to create like complex ETL workflows that are all with Hive or Impala or some SQL dialect. That's also to not have to orchestrate like hand-generated SQL is a big win.
For that slide you had with the data, looking at the speedups,
Yeah.
it looked like you had the peak separation at about 2,000 for the arrays on it. Is that right?
Yeah, I'm sort of. I will say. I was going to say something about that. I think it's an issue with my methodology, and I think that what's happening around here is that like garbage collection overhead, or like there's some kind of like memory throughput issue in like my benchmarking methodology that's causing a problem. So, and maybe like right around here, you've got like arrays that like nicely fit in like L2 cache, and it's like everything's fine. I don't know, like I'm not an expert there, but I need to publish the benchmarking code, and somebody will, I'm sure, sort that out for me.
So in that example you show for converting the large SQL query into multiple Ibis commands, is all the intermediate steps being passed back to the memory in your local machine, or is like lazy evaluate like when it happens in Spark?
Yeah, so they're all the expressions are. Oh, repeat the question. Yeah. So the question is in the SQL example with breaking down complex SQL into multiple statements. Everything you create is an expression, so it doesn't evaluate the expressions until you actually go to execute one of them. So everything is deferred. So it's the same it's the same type of model as Spark or other DSL type systems that you build effectively computation graphs, and then those get compiled. So I think that building Spark support into Ibis is also something that would be really interesting. So I think that the Ibis DSL maps nicely onto Spark data frame operations, and so you can think of like Ibis as sitting like one layer above API access to the Spark computation model.
Okay. Was it possible that you could have done this, what cascading did? Something at a SQL layer that other people also could leverage, and not just Python, but the general community, where you're at a distributed layer above the SQL, the JDBCs would pull in, and then you get access into it.
Do I need to repeat that? So the question is it possible to create a layer that can be taken advantage of by other querying languages or other environments? I'm not quite sure. I guess I would need to see like what that looks like exactly. I think so. One major artifact that will come out of this work is having a well-defined, efficient external way to extend systems with other code. So I'm focused on like let's make this work with Python, but for it to work with R and Julia or arbitrary code that you write that knows how to read and write the same tabular data format. So that's definitely something that is in scope. I also want to see the same tabular data format make its way into Spark, and so we can get faster UDFs in PySpark. So as far as like the SQL kind of generation DSL, like it's very coupled to the Python API. So and hypothetically, you could, if you wanted to generate SQL, you could like generate Python code which generates the SQL, and that might be easier to generate than SQL itself. So I don't see anything wrong with that, but I guess it's turtles all the way down. SQL's not going anywhere, so generating SQL's, a pretty good bet. But
Have you looked at the data frame that de-facto contributed to Spark?
I have looked at, this question is, have I looked at the Dotto data frame library? I have, and it's a very nice piece of software. It's about 150,000 lines of C++ 11. There's a lot of Python too. It is definitely, it's a large code base. It is definitely tailored for machine learning. So that in both like a good and a bad way. I don't know what bad is, but like if you look at it, it's like, yes, this is designed to be to maximize usefulness for machine learning. So I'm happy to see like better scalable, in-memory, out-of-core data frame libraries. And I've encouraged them. I've encouraged them to look at interoperability with the analytic SQL systems for Dotto's S-frame.
Would there be any practical limits in terms of the size of the data? And also, what do you estimate is the performance?
Well, the performance and scalability is limited by the underlying compute. So in a sense, like as Spark and Impala, big data compute systems get faster and more scalable, then tools like Ibis benefit directly from that. In the UDF case, where you're extending the system with Python, there will be overhead. I don't have an estimate of like what the slowdown would be over like hand-coded C++ or hand-coded Java. But the goal will be to like bring them as close together as possible. And I think that in like benchmarks of NumPy code versus hand-coded C, it's often able to get within a factor of 2 to 3. So that would be like our target, I think.
So how about latency from the perspective of the UI?
So I know that so analytic SQL, I like latency between like 100 milliseconds and a second tends to not be like that much of a priority. Between like 1 second and 10 seconds, is where like a lot of like the optimization and latency, like query throughput, is taken into consideration. So like systems like Impala, you have code gen that takes place. So like if you're operating on 100 terabytes of data, then like the code gen time of generating LLVM like specializations for a query like is relatively trivial, because the query might take tens of seconds or like minutes. But again, I think it depends on the data. It depends on what you're doing with it and the underlying how the data is stored, whether it's how it's partitioned, how is it stored? Is it Avro? Is it Parquet? Is it S3? Is it HDFS? How's your HDFS tuned? Like, there's a lot of factors. So.
I also have one more question. Is so would machine learning be a use case, or is that like not a use case?
It is definitely, and I think in general, to the extent that machine learning models can be rewritten or designed in a way that's amenable to the distributed model. So you have systems like MATLib, which are kind of in database machine learning. Spark MLlib, same thing. Like machine learning models rebuilt for sort of the Hadoop type architecture in mind. And so being able to access machine learning models from a system like this, because you'd like to be able to do your ETL, feature engineering, analytics, and then machine learning within the same kind of cohesive workflow without having to without having to like step outside the workflow to whenever you need to do more advanced analytics.
Are there any more questions? Should we wrap up? Well, let's thank our speaker.